I'm going to restart that recording. Let's get that recording restarted, baby.
Okay, one of the one he walked.
All right. All right.
I think they're pretty high because he based his entire thing.
That was an AV issue. That's what that was.
I know. I couldn't, there's no other contrast. I know. No time.
Demonetized. Let's get started. All right, everybody. Okay, so I haven't updated the attendance grades from Tuesday because I needed your lab sheets because they had your names, because that's how we took the attendance. I checked like at noon and there was still a group or two that hadn't, or there was one group that hadn't submitted yet. So hopefully everybody submitted their lab sheets by I saw that. She's such right. All right, so okay, so we need to after this though, my goal is to make all the 28-day data as quickly as available as quickly as possible. That should be posted later today. Homework 6 was due today. I thought I would give you the summary of a funny text exchange I had with our lab tech. I had an email from a student and said, having trouble getting the moduli of elasticity to match. So I texted, I said, is the calibration off on the Tenius-Olson? He said, oh yeah. So the moduli of elasticity that you compute from the lab data might be a little off. But I don't think that should ultimately affect the write-up that you did, but let's just say that I will definitely have some grace in evaluating that. It's okay. So homework 7 is assigned today. It's the last homework of the semester. I want to say two things about it. It's not due till dead week. It's due the Thursday of dead week. But I'll be totally candid, it's really short. It's a really quick assignment, and after today, you'll know how to do all of it, okay? It's really something you can knock out in a couple hours. So whatever you all decide to do, but the hardest problem on the assignment will probably be the one that we discussed today, and you'll see how it works. It's not hard, it's just there's a few step-by-steps because ultimately what we're going to talk about today are asphalt design methods. We're not really going to get into the specifics of the methods because they're very procedural, very step-by-step. I mean, if you understand how to do a concrete mix design, an asphalt mix design, I mean, it's not the same, but there's a lot of similarities with the rote proceduralism of it. But the one thing that's different are sort of the volumetric properties. And so if you understand how to compute those volumetric properties, you can work your way through the mix or the asphalt mix designs pretty easily. Okay, so that's what we're going to focus on today. Okay, everybody get the code? All right, I posted a video that I know everybody's watched. Yeah. And everybody's like, sure. Wink. Just kidding. All right, but I did post a video on asphalt. So the video that I posted, it was relatively short, but I was sort of talking about the asphalt binder, the actual sort of tar-like substance that is used in generating an asphalt pavement. I'll summarize a few key points from that lecture. So first off, I did differentiate a little bit between hot mix asphalt and cold patch asphalt. Has anybody ever used cold patch before, or maybe you or your parents, if they had like a little, rut or pothole in your driveway, you just go get a bag of cold patch and patch? Okay, that's fine for little repair jobs, but for large-scale highway infrastructure, we're not going to do that. We're going to use hot mix asphalt. The difference between the asphalt binding agent in a cold patch versus regular old hot mix asphalt is the asphalt has been broken up in one fashion or another, and I discussed two different ways that asphalt is broken down, either by what's called asphalt cutback or an asphalt emulsion. Okay, I don't really like asphalt cutbacks because the asphalt binding agent is broken up with a solvent, So the idea is you spray it, the solvent will evaporate and leave behind the asphalt. The problem is that this hydrocarbon solvent's evaporating into the atmosphere, so that's not good for Captain Planet. He's our hero. But the other issue is that the solvent can be flammable. So not only is it environmentally not as nice as using an emulsion product, but it's also could be a little dangerous. But whereas with an asphalt emulsion, just the asphalt particles themselves are broken up into these really, really small micron-sized globules, and then you spray it on, and it's really just water that's evaporating. So it's a little bit more eco-friendly. I talked a little bit about the various laboratory tests that characterize an asphalt binding agent, and then finally I discussed performance grades. And performance grades is going to relate to one of the problems on your homework 7, but essentially, so in the state of West Virginia, the performance grade's really easy to determine because it's just a lookup, it's just 6422. But when you look up performance grades for asphalt binders, the first number is the max temp that the asphalt is expected to perceive, and then the lower number would be the minimum temp, and that's in degrees Celsius, and the smaller number is a negative. So West Virginia uses 6422. Now asphalt is an ingredient in an asphalt concrete, or an asphalt, like a combination of asphalt, aggregate, and so on and so forth. So I want to talk a little bit about that process, okay? So if you're, if I use the term asphalt concrete, what I'm talking about is the combined mixture of asphalt, aggregate, and actually what is the most important ingredient, which I'll talk about here in a bit. There's another ingredient that matters quite a bit. But it is that collected mixture that ultimately turns into, like, the road surface and whatnot, okay? So what are our goals and general objectives when we're proportioning that mix? And again, that mixed proportion is very similar to a mixed design procedure in the way that, a lot of the computations are. But we're looking for stability, we're looking for resistance to permanent deformations, especially at high temperatures. We kind of want to avoid the whole rutting thing that we can get when you get high temperatures and the pavement can get a little soft. Roads are subjected to cyclic loading over and over again, so we do want to ensure fatigue resistance. We want to ensure resistance to thermal cracking under freeze-thaw cycles and even cycles of throughout just a given day. We want to make sure that it responds or resists various chemicals that go on the road, be it alkali, salts, and so on and so forth. We also want to make sure that it's workable, that it's going to be easy to place. The transportation engineers want to make sure that the surface condition of the road is such that we have enough grip between the road and the tire to provide, adequate friction for braking distances and skid resistance and things like that. So that has to be a factor as well. So the texture of the road matters as well. Ultimately, what you're trying to figure out when you do a mixed design for asphalt, ultimately the goal is you've got an aggregate, and it's usually not an aggregate, it's a mixture of several aggregates in order to get the proper blend. But the purpose is to try and determine the amount of asphalt that goes into that, okay? And the thing of it is that, it's a little bit tricky, right? Because if you get too much of the asphalt binder, you get less stability because it's got too, the binding agent can act as sort of like a lubricant as you're placing it, so it's almost like too slippery, okay? But if you got too little, it's not as durable and whatnot. So there's a nice little sweet spot. Typically, your asphalt content in a given concrete is going to be somewhere between 4% and 7%. That's a pretty good set your watch by range and whatnot. And you're going to be placing that at high temperatures, somewhere between 185 and 325 degrees Fahrenheit. Has anybody been on a DOH job where they're placing asphalt? It's pretty hot, isn't it? Yeah, so that's what you're doing. Okay, now the one, I'll go ahead and say it now because it's probably a good place to mention it now, and I'll be talking about this a good bit throughout the lecture. But the two ingredients that we are essentially proportioning together when we generate an asphalt pavement is asphalt in the aggregate. But there is a third ingredient inside the mix. And that third ingredient is air, okay? And a lot of the properties that we're going to be computing today, so whenever you go through a mix, whether it's the Marshall method or the superpave method, a lot of it's very rote, tabular, step-by-step. A lot of the computations that you're going to do are very akin to the stuff that we've been doing all semester. Computing specific gravities, computing weights and volumes, and so on and so forth. But there are some ratios that take a little bit of time to work through. Things like the percent air voids in the mix, the percent air voids that are, or the percent voids in the aggregate that are filled with asphalt, and so on and so forth. And that takes a little bit of work to go through. And so I think once you understand that, the process of going through and following the methods are really simple. Okay, now there are three methods that I just want to make sure that you're aware of. The most common one that's probably used today by most DOHs is what's called the superpave method. There are a couple of historical methods, which I'll mention just to make sure you're kind of on this, kind of aware of what's going on, and that's the Marshall method and the beam method. We don't really use the beam method around here, and I'll talk about why here in a bit. The Marshall method is a little bit more empirical. It's simpler, but because it's empirical, there's going to be a little bit more variance in the performance. But superpave is much more rigorous and much more performance-based. One thing I will say about asphalt design methods in general is that whenever you review the methods, so like in the case of superpave, okay, so you're gonna go through this process of selecting the aggregate, selecting the binder, determining the structure and the binder structure and all that. A lot of this, though, in order to properly design an asphalt, like really any of these methods, it requires lab testing, okay? And so one of the slight, I guess I would say, disadvantages of the superpave method is that you have to do much more extensive lab tests in order to characterize your aggregate, your asphalt, your mixtures appropriately. And that can be a little bit of a money sink in whatever lab's setting that up, okay? Do you get better data and a more reliable design? Well, yes, okay? All of these mixed design methods ultimately rely on some sort of testing. And that's not really anything hyper unique to asphalt. I mean, think about the mixed design that we did for concrete. I mean, ultimately, if you go through the process, we went through this big old volumetric design process and about 11 steps to get to the answer. But that was just really the first part. The second part was to go to the lab, test those cylinders, and adjust your mix accordingly, iterate as needed. Okay, it's the same idea here. Okay. Now, one thing I'll mention, I linked this. This is from Rowan University. There's a really good little PowerPoint that goes through step by step on how to do superpave if you're interested. It's pretty easy to follow, and it all works very well. What I'm going to try and do today is fill in the gaps on some of that stuff. The Marshall method is a simpler approach, and but it again also requires lab tests and whatnot. Now, the thing about about asphalt design methods in general, and the Marshall method is kind of a good way of doing that, or a good way of illustrating this, is that these methods are very repetitive. Like, you end up having to do the same computations over and over and over again. So they're very spreadsheet friendly, okay? So like what happens is, so like in the case of, let's say, the Marshall design method, what you're going to do is you got to do all of your aggregate evaluations, things like your specific gravity, your angularity, all of that whole blue. Got to do the same characteristic assessment of your asphalt binders. Then you need to perform a void analysis. That's what we're going to be doing today, okay? Once you do that, ultimately it's a lot of repetitive calculations. So you generate a series of graphs, and the way that you do this is you say, okay, let's assume an asphalt content of, let's say, 3.5%, compute a bunch of void ratios, the VFA, the VMA, the air voids, etc. Then let's do it again for 4%, 4.5%, 5%, and so on and so forth. So it's very spreadsheetable, if that makes any sense. And so you get a series of curves for each of these different ratios, and ultimately what you're trying to do is you're saying, okay, let's talk about the voids filled with asphalt. Well, dependent upon the asphalt content that you choose, There's a range that's too low, a range that's too high, and there's a range that works, okay? And so for each of these given ratios under a given mix design method, what you're trying to do is find the range where they all work, and then you say, okay, this range right here is the one that satisfies all of my criteria, so pick your asphalt content, you know, down there. And that's basically how it is. So once you understand how to compute these, it's a pretty straightforward process, okay? I mentioned the beam method just to be somewhat comprehensive in my discussion, but we didn't really use the beam method. The beam method is very empirical, and the only place you really see the beam method used is in the western part of the United States. There's a little bit, so it's a lot simpler, but there's a little bit less correction for aggregate properties and things like that, but the method sort of assumes some base behavior that you would get if you're doing the mix design in a given location, right? So that's why, I mean, I'm not saying there's anything wrong with it, I'm just saying, you know, it's like sometimes in engineering you will find that there are methods that work very well within their chosen constraints. And you take those methods and you start applying them out, that's when you start getting some problems. Okay, so in these discussions, okay, and like I said, one of the biggest things that you need to characterize in an asphalt concrete mixture is the voids, is the presence of air, okay? Now, the thing that makes this a little tricky with asphalt, and this is why these calculations can not really be like involved, they're just a little bit, like working around them can be a little bit strange. So ultimately we're going to need to determine volumes of voids or percent voids as a function of percent volume and so on and so forth. Volumes are really difficult to measure, okay? Weights are a lot easier to measure, okay? So what we're going to do is, so we know how to characterize each individual component. So what we're going to be doing for these volumetric void ratios is if we rigorously define them, we're going to be defining them as volume ratios. But volumes are difficult to measure. So we're going to sort of convert them to computations using specific gravities, okay? So there's a little bit of magic I'm doing in the background for that, but you'll sort of get what I'm talking about here in a bit. Okay. Now, if you've ever taken a course in geotechnical engineering like CE 322, this should look somewhat familiar. How many people in here have already taken geotech? Did y'all look at something like this? Does this look familiar? It should, right? Okay. So what we're looking at here is a phase diagram. Okay. So this is like one of the very first things that you cover in geotech. Am I correct? It's like probably week 1. Okay. For those of you that have not had geotech, I'm going to draw a soil phase diagram, sort of like over here on the board, and I'll kind of sort of relate it to this. So if you're doing, if you're looking at a sample of soil, okay. So let's say I dig up some soil from the earth, okay, and I say, okay, I've got some soil from the earth. What are its constitutive components? Well, in the case of soil, it's really going to be composed of 3 individual constitutive components at different percentages. It's going to have air, it's going to have water, and it's going to have solids. Okay? And then what we do for a given, and so like a very common exercise in geotech is for a given soil sample, if I give you certain data points, can you take that data and compute everything else? Okay? And so, like one of the things that we'll do in the land of soils is, so the way I always did it is over here on the left, I would characterize weights. And over here on the right, I would characterize volumes. Is that how you all did it?
Yeah.
Does that look familiar? Okay. So what you might do is, it's almost like drawing dimensions, right? So you'll say, okay, let's say for the weights, we'll call this dimension, if you will, the weight. Sometimes it's called weight total, right? And so the same thing over here, we'll have a volume total. Okay? And then what you would say is, okay, well, we have the weight of the solids, we have the weight of the water, And for those of you that had geotech, what's that dimension right there?
0.
0, because air does not have any weight, you know. Air does not have any weight. It has volume though, doesn't it, right? So over here we would have the volume of solids, we would have the volume of water. It does have a volume of air. By the way, for you soils folks, what was this dimension? Anybody remember that?
That's volume of voids.
The volume of voids. Remember that? And then so what you would do for a given sample of soil is try and characterize it, and then from these characterizations you're trying to determine various index properties for your soil. Like for example, if I were to say, what is the porosity? Anybody remember how to calculate that for a soil? For those of you that were in soils? Come on, what? What did you say?
I asked if they learned anything.
Covering the mic. Good Lord. I'm going to chalk it up to semesteritis. That's what I'm going to chalk it up to.
That's a good idea.
Thank you for the seconding of my strategy. No, is it like we just done with this semester, Dr. Mike? We're ready for turkey time. Is that what's going on? Okay. All right. So I'm prepping you this for 322 because you're going to see this a lot. And this is honestly, this is going to be probably the very first week of 322 when you characterize a soil sample based on the weights of the various weights and volumes of the various constituent components, and you'll use that to compute things like void ratios or porosity or whatever, right? And ultimately, those index properties lead to a number of things. It leads to soil classifications, either according to AASHTO or USGS or what have you. It leads to varying parameters related to performance, like we ultimately want to know for a given soil what's its cohesion, what's its angle of internal friction, all that, because that's what's necessary for geotechnical design. Okay, and so that's like sort of the whole point of the class. Okay, and it sort of starts with this. Well, we could do a similar phase diagram for asphalt. The phase diagram is a little different, okay, because we're going to have aggregate, we're going to have asphalt binder, and then just air. Note that some of that aggregate is going to be, or some of that asphalt is going to be absorbed into the aggregate, so we've got to account for that, okay? And what I propose that you'll find, or like what I want to focus on today, are the computation of 3 parameters that you see pop up a lot in asphalt concrete design, okay? And that is the VTM, the VMA, and the VFA, okay? So the VTM is the percent of air voids, or the abbreviation is the voids in the total mix. That's where the VTM comes from. The VMA are the voids in the mineral aggregate, and then the voids filled with asphalt. So this number is could be kind of high, but basically in a given aggregate, remember how aggregate has voids like that could absorb water. Remember saturating the surface dryer when all the voids are full but the surface is dry. Remember all that? Okay, so this is for a given aggregate, how much of those voids are filled with asphalt. Okay, now if I were to compute, let's say VTM, okay, VTM would be the percent of air voids. Okay, I propose that the way that you would compute that, and this for an asphalt concrete, would just be taking however much the volume of air is divided by the total volume of the mix divided by 100%, right? So that would be the percent of air voids. The problem is that computing these volumes for an asphalt is very complicated because asphalt is compacted. So if I take a section of asphalt that has this volume, I can compact it, and it has a different volume. So computing these ratios in terms of volumes is a little tricky. So instead, what's a little bit more accurate is to not express them in terms of weights, or sorry, instead of volumes, express them in terms of weights, or maybe more indirectly, in terms of specific gravities. Okay, so I'm going to throw some terms at you. Okay, so some of these terms you've kind of seen, some of them you haven't. Okay, so we're going to see these here in a bit. So the first thing I'm going to show you is this GMM. GMM stands for it's basically the maximum possible specific gravity of the asphalt concrete mixture. So when I say asphalt concrete, I mean binder, aggregate, all of that. Okay. So GMM is the theoretical maximum specific gravity, sometimes called the Rice gravity. So if you ever hear the term Rice gravity, what that means is that's the theoretical maximum specific gravity. In other words, like what would happen if there was binding agent, aggregate, and no air. That is as heavy as it could get. Okay. GSE, which we're actually not going to explicitly use here, but that's the specific gravity of the aggregate, and then GB, that's going to be the specific gravity of the binder. Okay. Now, I'm bringing up some stuff here that we've seen a while back. Do you remember? This was way back in the semester. Do you remember when we were talking about blending aggregates? Remember how we would say, okay, here's gravel 1 and gravel 2, and gravel 1, neither gravel 1 nor gravel 2 meet the specifications for a given job. But if I put a little bit of gravel 1 and a little bit of gravel 2 all together, suddenly I've got an aggregate that works. Y'all remember that? And remember how all of the properties were computed as a weighted average other than the specific gravity. And remember how we compute the specific gravity is we take 1 divided by the sum of the percentage of a given component divided by specific gravity. Y'all remember that? We're going to do that today. Now, I'm going to slightly adjust it a little bit. What I'm going to do is I'm going to call this 100% because I'm going to express these as percentages. So the top's going to be multiplied by 100, the bottom's going to be multiplied by 100. We're going to see that here in a little bit. Okay? All right. So what I'm going to do for each of these ratios is I'm going to compute them as, instead of with volumes, I'm going to compute them with specific gravities. Okay? Now there's a couple terms that we're going to go through together. There's the bulk specific gravity of the aggregate. There's the maximum theoretical, the Rice specific gravity. Then we're also going to need to calculate the bulk specific gravity of the mixture. Okay? It's not hard, but there is a little bit of bookkeeping that's involved. So let's explain that bookkeeping with an example. Okay, so I have a compacted specimen of hot mix asphalt. Okay, so let me just sort of set the stage on what's going on here. Okay, so I have prepared a mixture of hot mix asphalt. Okay, now I prepared that mixture with 4 aggregates and a binding agent. So there's aggregate 1, aggregate 2, aggregate 3, aggregate 4. So if you notice here I have on the board, this is that data that, I was looking forward into the future. I went ahead and wrote it here on the board. Okay? So the total weight here, like this total weight, if I sum this up, that total weight is something like 5.51 pounds. Okay? From this mixture of asphalt, what I did is I drew a sample. I drew a sample of about half of it, and I compacted it into a test specimen. Okay, so I drew from this sample a specimen that weighs 2.55 pounds and has a volume of 30.5 cubic inches. Okay, so we're going to use that a little bit later. But what I want to determine, ultimately my goal is to determine these volumetric ratios. Okay, but in order to determine these volumetric ratios, I'm going to need to determine these specific gravities. Okay, so let's go through this. Okay, so okay. All right, so there's several properties that we need to compute, and so I'm going to take each property one step at a time. Okay, so the first property that we're going to compute is the bulk specific gravity of the aggregate. Okay. and the symbol for that is GSB. So this is before we're taking this aggregate mixture and putting it into the concrete, or into the mix. We're just taking all these 4 aggregates and trying to treat them as one. So this value, again, so like we've got 4 aggregates, I just want to treat it as one aggregate. So I need a specific gravity of the mix, okay? And the way that we're going to compute that is a fraction. We're going to take 100% times the sum. I can do better than that. PI. GI. This is going to be how we're going to do that. Okay. So how do we go about that? So we have our components. Oh, sorry, wait. I'm getting ahead of myself. Okay, so I'm looking at the aggregate right now. So I'm actually just going to list the aggregates by themselves. I'm going to do the binder later. Okay, so the weight of these is going to be 1.76, 2.43, 0.77, 0.33. Okay, so I'm actually skipping the binder right now because I'm just trying to characterize the bulk specific gravity of the aggregate. Okay, so if I sum these up, I'm going to sum these up and I'm going to get 5.29. Okay, now that's different than this, but again, this is including the binding agent. I'm not looking at the binder right now. Okay, now, next thing I want to compute is a percentage. Okay, so let's just pop quiz everybody. So the total amount of aggregate in this mixture is 5.29 pounds. Aggregate 1 takes up 1.76 pounds. How much is the percentage? How would I calculate, like, is this 20%? Is it 30%? How much is this part of the mix? 33.27%. And so you basically just took that and divided it by the sum. Now, I'm multiplying it by 100 just to make the numbers a little bigger and make them a little easier to deal with. Is everybody okay with that? And if I kept going, this is going to be 45.94, 14.56, 6.24. Okay? Let's just have those there. Okay, so if I sum those up, that should be 100. There we go. All right. So now I'm going to list the specific gravities. So I got something on my screen there. So the specific gravities are 2.62, 2.51, 2.47, 2.42. Okay. So now that I've got that, what am I going to do with it? Okay. So ultimately, I need to take 100 and I need to divide it by this sum. And that sum is going to be the sum of these fractions. So let's calculate that fraction for each row. Okay. So let's take a PI divided by GI. And what am I doing? I'm taking this divided by that, this divided by that, this divided by that, this divided by that. So that's going to give me 12.699. Is everybody okay with that? This is going to be 18,301. Bless you. 5.893, 2.578. Like, is that okay that I just did that, or y'all comfortable with that?
It's just the percentage divided by the specific gravity.
Yeah, just that. Bam, 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 bam. Yeah, so like this one's 6 and change divided by 2 and change is what about 2 and change. So. All right, and so if we sum this up, we get 39.470. So how do we calculate the bulk specific gravity? Just divide the two, and that's going to give us 2.534. Okay? Now, I want to be clear, this right here is actually something that I expected everybody in the class to be able to do prior to coming in, because we've done this problem before. We actually did this problem earlier in the semester. So this is nothing new, okay? So let's just put that on the board, just so that we have it. Okay. All right. Is that easy? Everybody okay with that? All right. So that one's easy. Okay. What about the next one? Okay. So the next thing we're now going to compute is theoretical maximum or the Rice specific gravity. Okay? Now, this is going to feel really redundant, but that computation that I just did, I'm going to do it again. Okay? What's going to change? What's going to change is instead of looking at aggregate 1, 2, 3, and 4, now I'm going to look at aggregate 1, 2, 3, and 4 and the binding agent. So essentially, I got to do this calculation all over again. Okay? Now you might think, what changes? Well, just bear with me. Okay? Okay, so let's record our weights down. Now here's the thing. The sum at the bottom is now different, okay? Before, the sum was 5.29, okay? Now the sum is going to be 5.51, okay? So what I'm getting at is because I now have a new ingredient, each one of these percentages are going to be ever so slightly different, okay? So, and I've got another ingredient, so basically I have to do that specific gravity calculation all over again, just with a new ingredient. So, take 1.76 divided by 5.51. Take 2.43 divided by 5.51, etc. Okay. All right. And then we've got our specific gravity. And so now I'm going to do the same calculation. And yeah, it's kind of a dry set of computations. Okay. Now, I'm going to leave a little bit of space right here for a reason. Just bear with me on that, okay? All right, so how do we calculate our GMM? And it ends up being 2.400. Okay. So, let's just take a look at the data, okay? So this is the specific gravity of the aggregate. This is the maximum possible specific gravity of the asphalt concrete mixture. Now, why is it less? Well, it's because we added a binding agent that's not very heavy, so that's going to drop the overall specific gravity. But this specific gravity assumes no voids in the mixture, okay? And so when we calculate GMB, which is the specific gravity of the sample that we collected, it's going to be less than 2.400 because it's got air in it, okay? So you're going to see that here in a bit. But I'm not done with this, okay? I'm not done with this. We're going to see a value pop up in a later calculation, okay? What did we say this column right here needs to sum to? Like if I put a sum right here, what does this column have to be? 100. Okay. All right. I'm going to group this in two different groups. Okay. I want to look at this group. And I want to look at this. Okay? I'm going to call this PB, and I'm going to call this PS. Okay? So I'm going to say note, PS is the sum of PI, which is 96%. It actually does end up being 96%. There's like a little bit of decimal round off value, like you'd think it'd be 96.01, but there's rounding in there. But I'm just putting that calculation off to the side because we're going to see that value pop up later. So what I'm proposing is that this asphalt mixture has about 4% binder and 96% aggregate. Okay? So we'll just say note, PS is 96%. Just keep that in the back of your head. We'll use that later. Okay. Okay, everybody get that far? Any questions? Okay, so next thing I'm going to compute is this. Okay. And so, just to sort of explain what we're doing here, remember, ultimately all of these voids are trying to make sure that we're fully characterizing essentially the air in the mix. Okay? Now this GMM value is what the specific gravity of the asphalt mixture would be if there was no air in it. But we drew a sample, and that sample has air in it. So how are we going to figure that out? Well, what do we know about the sample that we drew? Okay, we know the sample has a weight of 2.55 pounds, and we know the sample has a volume of 30.5 cubic inches. Now, how do we measure unit weights? How have we been measuring unit weights? The unit weight of water is 62.4 what? I know you all have fluids. I hear about it all the time. Unit weight of water is 62.4 pounds per what? Come on, don't be shy. What?
Cubic inch, pounds per cubic inch.
Cubic feet. Come on now. I hope that number has come up. You use metric?
Yeah.
Okay. 9810. Kids with your kilograms. Okay. Okay. We need to convert this into pounds per cubic feet. How do we convert cubic inches to cubic feet? How do we do that? What?
Metric.
We're not in metric land. We're in U.S. land.
I do it.
How do we do this? How do we convert cubic inches to cubic feet?
Do you multiply by 12 cubed?
Do you multiply or do you divide?
I don't know, I'm asking you.
I'm asking you. I know the answer.
I'm the one sitting over here, I don't know the answer.
This is how you learn. Which is, you multiply, I mean, hold on. So, hold on. Think about it like this. How big is a cubic inch? It's this big, right? This big. A cubic foot's like this big. So if you have this many cubic inches, you don't have this many cubic feet. You have a smaller amount of cubic feet, okay? So what I'm saying is you're going to take 1 foot cubed divided by 12 cubed inches cubed. 12 cubed is 1728. So if I take this and I divide it by 1728, I get 0.01765 cubic feet. Okay? So from these, now how do you compute the unit weight of the mix? What's the formula? You don't get away with this. This isn't the units question.
Does that say 12 cubed cubic inches?
Yes. Yes. So, because it's 1 foot cubed over 1728 inches cubed. Now, how do we compute unit weight?
Weight over the volume.
Weight over the volume. There we go. You didn't really want me to bring up fluids again, did you? Come on now. Y'all are done with this semester, I can tell. Y'all are just done. We're almost there. Look at this. After today in this class, we only have 3 more lectures. And one of them is just Q&A on the lab report. So, I mean, we're almost there.
Can you say that louder, Cole? Say it, go ahead.
I think he's expressing joy.
This class is not the problem, is what he said.
The answer is 144.472. And the units are pounds per cubic feet. I understand, let's be clear, I understand the ease of computation and the dimensional consistency of SI. But when you go to Lowe's or go to Home Depot, they sell 2x4s. And until they start expressing that in metric, you are civil engineers and you need to learn how to deal with US units.
Take it up with the other professors instead.
We are in this class. We are talking about this class.
I agree with what you're saying, but wouldn't our curriculum need to be consistently in American units then, if that's what we're going to learn?
No.
Although why are they teaching us metric if they're not gonna sell metric at Lowe's?
Okay, what if we use traffic?
So,
I'm not going to work.
you know, hey, I'm gonna give you an answer. You know what Lowe's and Home Depot also sells? Socket wrenches and millimeters.
Yeah.
Oh.
Mechanics.
Oh.
Those star tools.
Bring your translator.
Boom.
Bring your translator in the Lowe's.
I'll have to bring my
Marker
computer to
drop.
Lowe's.
Okay. Okay, all right, everybody. All right. So, okay. In general, how do you compute a specific gravity? Like, if I have a specific gravity of some material, how do I compute that? Like, if I have a unit weight of a material, how do I compute a specific gravity? What do? I take it and I divide it by something.
The water.
The unit weight of water. And this is GMB. Okay? That's what this is. GMB is the specific gravity of the sample that we drew. Okay? And I propose it's a comparison of the unit weight of this mix to the unit weight of water. Okay? And water has a unit weight of 62.4 pounds per cubic foot. And we use that value in here. We use that in the mixed design of concrete. I'm like, I didn't know what it is. Do I? We used it in here. Okay. And what do we get when we chug this out? We get a value of 2.315. Which again, it's going to be less than this because this is as high as it can go. Okay. So these are our three specific gravities, and we're going to use these specific gravities in order to compute our three ratios. Once you get these specific gravities, our three void ratios are pretty simple to compute. They're not hard. Okay? Okay, everybody got this? Metric and US units. All right. Okay. First thing we're going to compute is the percent air voids in the total mix, which is called the VTM. And the VTM, so here, let's see if we can reason through what the formula looks like. Okay? So first off, I'm going to want this as a percentage, so I'm going to multiply it by 100% on the outside. Okay? And what I'm doing is I'm basically saying, let's see if we can reason through this. So this is the specific gravity of the mixture, and this is the maximum possible specific gravity. So the difference between the two is the fact that there are voids in it, right? And we're talking about a percent change. So essentially what I'm doing is the change in specific gravity over the original. It's like a percent change in an experiment. So one way that we could compute that is we could say GMM minus GMB over GMM, right? Theoretical minus expected, all over, right? But we can separate that as 1 minus GMB over GMM by just recognizing that GMM over GMM is 1. And what is the formula? The formula is 1 minus GMB over GMM. That's it. So it's a pretty straightforward calculation. And the way that we compute that is as follows. Okay, so when we chug that out, we get 3.54%. So what that's saying is that 3.54% of the volume is air. Okay? All right, so for this next one, the next ones are Video Music Awards, or sorry, percent air voids in mineral aggregate. Okay? I know, I'm a dork. Okay? Now, the way that we compute that is we basically say, okay, let's start off with 100% of the volume, and let's subtract out a fraction. Okay? What is that fraction? Okay, well, on the denominator is GSB. In other words, the total amount of just aggregate specific gravity. And on the top, what we're going to do is we're going to take our mixed specific gravity, but we're not going to take all of it. All we're interested in is how much of that is occupied by solids, how much of that is occupied by aggregates. Okay? So it's essentially, again, it's a 1 minus, okay, with the percent, the 100% factored in. So it's sort of in the same fashion as this. The only difference is I'm adjusting this by, all I care about is how much of that is solid. Okay, so it's 100% minus a fraction, 2.534 on the bottom. And of that, I want to know how much of the asphalt mix is solid. So when we chug that out, we get 12.30%. So our Video Music Awards is 12.30%. Okay. Last one is we're trying to figure out how much of the voids are filled with asphalt. Okay, and what we're going to do here is now essentially what we're doing is we're comparing these ratios. Okay, so VFA is, you know, if you want, you can write it like this. You can say 1 minus VTM over VMA. You can do that. And so of all the voids present in the mix, how many of them are filled with asphalt? That's going to be 71% or 71.22%. Okay. So now I'm just going to write down all the values. So Okay. Is that too bad? I'm hoping that's really easy. I'm hoping that's not very, very challenging. And again, if you start going through mixed design procedures for asphalt, you know, like I said, we didn't cover them, but I mean, I think it's worth it to sort of like just peruse the textbook, take a look at them, and what you're going to see is a lot of really, really familiar calculations mixed with these, okay? And so once you know how to do these, it's really not that hard. I mean, I think part of being an engineer is learning how to do stuff you've never done before. I want to provide you the tools necessary to figure that out, but we're not going to teach you everything. So once you understand this, I think you can work through it. So that's all I got, everybody. You're getting 10 minutes of your life back. I will see you all on, well, tomorrow.
You don't have to sound so excited.
Well, I was saying Tuesday, but in here I'll see you Tuesday. I'll see instructors tomorrow, so.